Hello, everybody. So, got a few things to go over tonight. Mostly talking about arrays, which, based off what the prerequisites for this class are doing, there's something you would have called arrays that aren't really arrays. So in Java, we have actual real arrays, so there might be a few adjustments to make from what you're used to calling that, using that word for it. Which I did shuffle the schedule around, and we'll look at those things probably on Tuesday. That way, I would like y'all to take a couple days to work with the actual formal arrays because they are different than lists. We avoid the word list because that has so many common everyday uses for us, right? Grocery list, the to-do list, all the different places that shows up in normal English, which are all very different than the thing that's equivalent, that's sort of the counterpart to an array, the actual computer definition of list. So to avoid that confusion, we just use array as our catch-all term, even though we use lists a lot more often than arrays. So I was thinking, go over arrays tonight, and you got a couple days, weekend to write code and practice things. It's an active subject. We learn by doing stuff, having code. So tonight, after the lecture portion, and then through the weekend, as you're getting random practice, please practice with regular arrays first, the rigid ones, non-dynamic structures, because the prerequisites for this class, we just called something arrays. We didn't actually work with arrays. So there might be a few little details different than what you're used to. And then next Tuesday, we'll look at a couple types of lists that are going to be what you're used to work, more like what you're used to working with, the dynamic structures. We can add things to them, take things away. If we need to add something to a list, we don't have to make a new list and it's a little bit bigger and copy everything over. So a few finer details of working with actual arrays. The trade-off for that is an exaggerated version of what we get from the strictly typed language. It's going to be much, much faster. The computer doesn't have to waste any resources trying to figure out how much room we need to store stuff. And when we get to the list next week, I will throw some numbers out there as far as how much is going to be wasted when we just to keep that thing dynamic. When we have an array, if we say, okay, we need to store 8 bytes sort of data, 8 elements of byte data, the computer is going to give us 64 bits, period, at 8-bit chunks. And we cannot change it or anything, but there's nothing wasted, so we get a lot of speed off that. It's kind of like the advantage we get from the strictly typed language over the open type language 8 times over in that case. So there's some advantages to it. I guess I'll start with my normal little analogy I like to use for arrays, because in a classroom, we're very restricted for time. It's even more exaggerated in the introduction class. In the SDEV 120 class, right, we've gone over, talked about arrays, actually used lists in the language. In that class, you were either using Raptor, which is written in Perl, and Perl is like Python, it has lists and doesn't have actual arrays. Or you would have been using Python, and you cannot have an actual array in an open type language. So, and SDEV 120 is the list, but we talk about them and the small things at the introduction level. It's almost impossible to see the advantage of it. Past the introduction level here, right? For at least 3 classes in to the programming degree, but we're still in a classroom. We're still under tight time constraints. In our class, this is still one of the 16-week classes, so we have more time than a lot of the other classes, or what this course will have going forward. But we're still very restricted on time relative to the size of the Java programming language and the stuff we can do with those tools. So one thing in classrooms, all the homework assignments, and I believe this module, it might be the next module, you'll submit your proposal for your final project. And I've never rejected a final project for not being big enough. Every time I've ever told somebody this isn't going to work for a classroom project, it's because there's some subtleties in there that are going to grow way too big to handle in a 16-week course. So things that you might not see at first. One of the best examples is if you're putting together a GUI package and like not using the GUI package, actually making it from scratch, right? Making the package that people are going to use to build GUIs. You open a text box. That's no problem at all, right? Straw box, like any rectangle, we only need 2 corners to define it. That goes in like easy as can be. You need the letters, the symbols, the characters from the keyboard. It's not bad, there's going to be a lot of them, but when we define what the pixels are going to do to make that picture, it's still a fairly small task, a reasonable task. It's something we can easily handle. Even if not by pixels like SDEV graphics and draw a bunch, we can easily handle a bunch of lines to build up and make a letter and get the letters in there. That's no problem. All that stuff's coming together easily. But when we make a text box, one of our expectations on there, I put her name on the list before. One of the expectations when we make a text box for a GUI package somebody else is going to use is that there's going to be a little blinking cursor there to tell us where we're typing. Right? Type the first letter, that cursor moves over. Type the next letter, that cursor moves over a little. Oh, got to do some editing, so you click and move that cursor back, and then the user knows where they're going to type at. That is a big deal. You probably wouldn't think about it if you just said, okay, I want to make a GUI package, put a text box there. But in order to do that cursor correctly, you have to know in advance the size of every letter in every font that you will allow people to type in, which is a really, really big deal. Okay? A lot of things to predict. So sometimes the little subtleties like that will, those little subtleties will be in there, and then what you thought seemed like a small project, there's a little subtlety that I'll see whenever I read the proposal and be like, okay, that's gonna, there's some small things that are gonna suddenly escalate in the background value on that. So I've never rejected a project because it's too, I feel like it's too small. Everybody usually has good ideas, but I have rejected project proposals in the classroom because there's some things there that would be way too big to fit in even 16 weeks. We're very restricted on, time in a classroom. So any assignments and stuff we do are carefully designed in advance to fit within those time constraints. So even though we're past the introduction level, or what started this little spiel here, since I've kind of drifted off into a couple other things multiple times, I think, let's start this at the introduction level. It's almost impossible to see the usefulness for arrays. Back in the SDEV 120 class, it's like, okay, this took even more typing than just storing this in variables. Why not just do that? Or, and maybe in the SDEV 140 class, you might have done something a little bit bigger and we're like, okay, this is a little more useful. But really, unless you have thousands of data points, it's really hard to see the advantage of working with arrays over a bunch of variables. Because anything that fits in the time constraints for classroom is going to be small enough to fit in a classroom. So you're not going to have those huge, huge things where the advantages of working with collections really start to show up. So I'd start off with a little analogy, a way to think about it that because it's hard to see in our classroom setting because of the time constraints. Move this over. So a trip to school, right? Heading up to school for a day of going to classes, taking notes, all that stuff. We're gonna need a few items. Right? Maybe needing a notebook. That's something we'll need for day of school. A couple folders here. Stack those on there. A calculator, might need that. A pen and a pencil. It's probably hard to see these on the camera. That's why I'm rattling them off as I get there. Pack of gum, I grab that. Oh, drop the pencil. Oh. Dropping some stuff as I pile it up here, but got the phone charger. I've got the computer charger too, because I was expecting to drop stuff, so I figured I'd leave the computer out of the pile and just imply it. Well, that works fine. There's the stuff I need for a day at school, right? And I can pile it up, carry it around. All the stuff I need is right there. There's no problem whatsoever. But there's a better way to do that, right? If I'm heading to school, probably going to carry this with me, right? In which case, throw this over on my camera. Instead of just this pile of things, I can just stick all this in the big pocket on the backpack. And have this one thing to carry. And my hands are still free to do other stuff. I can carry all my stuff while my hands are free to do other stuff. It's all in the backpack. And whenever I need stuff to accentuate the process, I get to school, carry your backpack down the hall, head into your math class. Okay, you're gonna need a notebook and a calculator and a pencil for math class. That sounds reasonable. So you can go to your backpack and say, okay, look at each item one at a time. Is this the calculator? Nope, not a calculator. Grab the next item. Is this the calculator? Nope, not the calculator. Grab the next item. Is this the calculator? Nope, it's a notebook, so not the calculator. What's next? Is this a calculator? Oh, there's a calculator. So that's the thing we need. And we'll kind of go through everything in the backpack. We're an intelligent species. We don't have much, we do it at a glance, right? We open our backpack and grab the stuff. But accentuating the point here, right? There's one of the things. What's next? A notebook. Already saw that. Would have been useful to grab that the first time. But go through the stuff again. Is this a notebook? Nope, it's a computer charger. Is this a notebook? Nope, it's a folder. Is this a notebook? Yes. And go through all of our stuff one at a time, find them, and ask that question. Is this the one we need? And we pull it out of the collection. And I like to talk about that analogy because in the time constraints of a classroom, it's really hard to see the advantage of working with collections. Most of the stuff we do that fits in the classroom, it's going to, at the best, it's going to be the same length as if we would have done that in variables. Right? We're not gaining anything when we have a small program that fits in the time constraints of a weekly homework assignment. And we could have just listed out that many variables. And in a lot of cases, in the stuff that we can look at here, it may even have been easier to use the variables than a collection. Because this is going to extend to all our collections and all our data structures. We have a whole bunch of data structures to look at this semester too, once we get to the interesting part. We're still in the basic syntax. I guess the first interesting thing, extension, the first big step beyond what you've done in the prerequisites is going to come next week. So we're almost to the just fundamental syntax now. So I like to use that analogy to help show where it's useful for. And a backpack's a great one because that point of carrying the stuff, I carry that fine in a pile, but when it's in a backpack, I can carry it and still do stuff with my hands. So there's like a doubly large advantage, but really when we're programming, we don't see that advantage till we get up to thousands of elements in our array, or several arrays with thousands or tens of thousands of elements each. Until we get there, at that level, which is not going to show up in a classroom, obviously, it's kind of hard to see that advantage. Yes, a great comment in there with the analogy, the stuff in the backpack, you might forget what all's in there. Something will poke you in the back and then it's bouncing like it hits your back all the way down the hall. So you can either stop and adjust it, you have to stop and adjust it somewhere. Or I remember one particularly hefty semester, I had to tie my shoe, and it was a brand new set of shoes. They had extremely long shoelaces on them. So it was something that I didn't even want to walk the rest of the way across the parking lot with. But it was a very busy semester with some very, very big books. Several books that were like that thick. And when I bent down, tied my shoe, and then went to stand back up, I didn't come back up on the first try. I mean, it wasn't so heavy that I couldn't get back up, but it caught me by surprise. It was more than I was expecting. So there's things like that with the backpack. And it's an analogy, a comparison, a way to hopefully help see this while we're in the setting of doing things and while we're in the classroom setting. Before you get out there and encourage you to work with collections more. Even if it seems like variables would be easier in a particular situation. That's why the homework this week not only says, it also says which collections to use. Actually, it's the same homework twice. You'll do all the assignments with regular arrays, the one we talked about tonight, and then you'll do all the same assignments with lists. I thought that would be a good little way to compare them and see what's similar and what's different. So I pull stuff back out of my backpack because I had notes and things like that. Might need to, yeah. That's probably all I need. Once again, I probably barely look at my notes. This is the 4th time I've used these notes, I think. So I know what's in them, but it's probably coming on time to rewrite them. There's all kinds of little side notes in the margins and stuff from every time I've used them. But arrays. What I put in here so far, kind of brushed through the syntax and things. Okay, we went through a lot of that really quickly. We stretched out a couple nights just talking about Java in general, looking at JSP pages. I want to make sure and include that. We're in the transition phase. I mentioned that the other day. You all learned that phase. I'm saying do your homework with both the main method and the JSP page. Switch back and forth between them. Or what we looked at the other day, we're always making objects, so just import that out, do a main method, and then import that object over to a JSP where you can use it. Because moving forward in the world, every day more and more things go to the cloud. So you need to get some practice on stuff that's going to run on a server and be delivered to a user through their web browser. But we're not there yet. So we can't leave the main method behind. So y'all are in one of those transition phases where you need to see, where you kind of need practice with both of them right now, learning language right now. We still rush through it. But this one, I guess is going to go kind of quick, but slower than the other stuff. So we're going to look at arrays. There is a technical definition for it. That's showing up on the board, okay. I change my view so I can see what's, okay, yeah. So arrays are consecutive memory locations allocated to store data of the same type. So a very strict definition there. Here's the reason we don't have arrays in Python, the language you would have seen as the prerequisites for this. So that's an open type language, but we're in a strictly type language. That's also a big advantage when we know that, because we don't waste any resources tracking. We know the computer knows ahead of time how many resources to dedicate to everything we ask it to do, down to the exact number of bits. So more fine-grained control is more control. We have more control over how well the stuff is going to work, how fast it's going to go. That's usually the one we care about, the speed, right? But maybe we want to worry about resources. And we know it's going to be on a system that has lots of stuff running at the same time. Okay. Company that we know everybody in the company is going to be on Microsoft Teams and what's the other chat one? Snap? No, not Snap. Starts with an S. The other popular business chat room. Can't remember the name. Everybody in the company is going to be on a couple of chat rooms. They're going to have Microsoft Office, Microsoft Word, Microsoft Excel open. Be working on a slide deck, maybe even 2 slide decks. They have a bunch of meetings scheduled coming up. They're going to be running all of that software at once. So we want things to be fast, but we also want to be very cautious with our resource usage. We don't want to use any more RAM than we can, because that's going to slow everything down. Not just our software. If we try to use too much RAM, that's going to slow down all that other software they have running at the same time. So you might want to optimize not for speed, but for resource usage. And I'm hinting at these things now because that's going to be a big deal. I think week 12 is when we're going to first look at telemetry and metrics. Up in November. It's still a few weeks away, but hinting at it now so that it's in your mind for why we do that sort of stuff. Consecutive memory locations that's a big thing with arrays. We always know exactly where they're going to be at. I don't think this marker has much left in it. So I'm gonna kind of draw a stack heap diagram and talk about this some. So I've drawn these I use these pictures a lot. On one side is our stack, and have a clear defined starting point. Then we stack up instructions and then take those instructions one at a time and run it. That's kind of what a machine does naturally. So it's a good one for resource usage. And over on the other side is a data structure called a heap. And we'll talk about both of them in detail later this semester. But heap is optimized for speed. It is the fastest data structure. So our RAM chips almost always set up to use a heap unless we come back and override that. Because it's the optimal one for speed. So we're usually using these 2 data structures when we process. That's like the default unless we go in and change. So I'm gonna draw a couple pictures on stack heap diagram. So first off, I don't think that black marker is going to last much longer. Might have to switch to blue. Can everybody see colors okay? Are there any markers, any colors I need to throw in the trash can? See head shaking, no here. I don't hear anything on the chat. Don't see anything in the chat room. Okay. I always like to check. I don't know how that fits in as far as private information, but if somebody's colorblind, I don't want to be up here writing in a color they can't see. That could be a big deal. So if we have an array over in our code, it's going to point to some spot in memory where over in RAM, where the data that we're currently working with is held. Maybe RAM, maybe the registers. There's a distinction between the 2. RAM holds the current program, and registers hold the current step of the program. But yeah, otherwise they're the volatile storage.
our temporary storage where we work at, the ones directly connected to the CPU, if not inside of the CPU, if not built into the CPU. So we're going to store data in consecutive memory locations. So maybe we have some byte data. That's easy to do math with. We have a bunch of bytes, and to indicate we have an array, we'll put square brackets between the, so it's still part of the type declaration. So an array of byte data. I already wrote it on the stack, so I'm going to call that ARR equals a new array of byte data with maybe 4 things in it. It's going to look like that. We'll see that a couple times tonight. But then what the computer's doing, it's going to put those in consecutive memory locations. First one might be chosen at random. Yeah, consecutive is Java specific. There's an older definition. Let me put that up here. Instead of consecutive memory locations, I can't think of a way to put it in a full sentence there. So with a recursive algorithm, the recursive algorithm. So it's using the same formula to store them all the time. I'm going to go use this for the first picture. I'm going to use the old style one. So maybe our recursive algorithm is something like 3 times the size plus 22. So we have our start point. Whatever bit we start at plus 3 times our size plus another 22 bits is where the next one's going to start at. So maybe our first one here, which I wrote byte because then we can just say this is a little block of 8 bits, and maybe it starts at memory location 100. Hopefully that won't be too bad with the math. I just made up the recursive thing there. So element 0 starts at 100 plus 3 times the size, so 3 times 8 would be 24 plus another 22 will give us 46. So our next one, after that, we come over and reserve another 8 bits, which is going to start at bit number 146. So we plug that back in. 146 plus another 46 is 192. We'll come over to set out an 8-bit chunk starting at bit 192. And another thing, notice how I'm listing these out. That's another one we don't have a lot of time for in the classroom. That's why I like to do it on the board so that y'all are aware that it's something that we can sit down and calculate on paper without much trouble. But it doesn't fit very well in the time constraints of the classroom. Not going to show up much on weekly homework. Mostly just so you know that we can calculate it. And there's another one there, but I think y'all see the pattern, right? We go to our start point, stick our 8 bits of data, and then figure out where the next one's going to start, and then the next one. And way back in the day, algorithms like this were very important. Like back in the 50s and 60s, the early days of computing. Like when we used, actually had heating coils and the vacuum tubes. Because, well, there's a heating coil, it gets very hot very quickly, right? And if we turn on 8 heating coils right here, some of that heat's going to drift over and affect the ones right here, or right here. Or if these are too close, like right there in between the way it's drawn on that picture, some of those switches would get heated up and come on inadvertently. So back then it was very, very important to kind of spread your data out. But that was a long time ago. We use transistors and stuff now. That's just part of the definition. That's where consecutive memory locations, we always use that in Java. So our algorithm isn't something fancy like that. It's start plus size, just the next 8 bits. Because we don't use heating coils anymore. It doesn't matter at all if we turn on the next 8 transistors. They're not going to affect the 8. They're not going to affect the transistors around. If it's laid out properly. There is some of that that still happens. It's called phantom transistors. When we pack that many things close together, from the way they work, it's possible to inadvertently make extra transistors because of like one sitting this way and the other one turned around facing the other way. We accidentally created another transistor between those two because of how they're oriented in there. So there is some of that. There's still some crossover still, but that's for the electrical engineers to deal with. It's usually pretty well worked out by the time it gets to us. So we can go with the easier algorithm, but we still do that recursive algorithm. The first one starts at bit 100 plus size, so the second one's going to start at 108. And the third one is going to start at 116, 124. We just use a big chunk right next to each other, which is something else to worry about because then we are using a big chunk of memory right next to each other, consolidated together, which is we have a big thing blocked off and reserved for us that other stuff cannot use. Usually not much of a problem, but as things get really, really large, it could start affecting other things that want to use that RAM, especially with parallel processing and multi-threading, where we'll have multiple things going on at once, like any modern computer, right? Usually have a lot of things going on at once. So things like that can add up, and there might not be a bug in your software, but your software could be causing bugs in other software as well. So as things grow larger and larger, you have to remember to check for that. It's like, okay, my software works great, but does it work great if I run it at the same time as Microsoft Word? So like bleed over debugging, which is usually situations like this where we reserve too much RAM and then the other software can't do anything until ours stops. Another thing, I'll put it up on the picture here. I'm going to erase some of the middle of the stack heap diagram. Is that okay? Just sort of going over what that was about. This picture gets very cluttered if I don't erase it. In past semesters, I have to try to keep drawing more and more stuff in RAM, and it gets to be a mess after a while. So we have this array. I'll use the same one. An array of bytes. That way it's nice and easy to work with. For 4 chunks of 8-bit data. And there's 4 chunks. There's 4 of them. So 1, 2, 3, 4. And each one has 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So a whole bunch of bits going on inside there. That was supposed to be blocking things off, not ones, but it probably just looks like a thick line drawn there on the video or something. The 8 bits. So when we ask for it, we're pointing at the beginning. So to ask for that, we need to say, well, we want that array collection, but we want a particular one out of there. And we want the array plus nothing. We want right there where it starts. So array 0 is exactly at the initial starting point. And we have this discrepancy. When we ask for data, we ask for the beginning of it. But before we can say we have one element, where we would count that we have one element is 8 bits further over in that. So there's that discrepancy between the one we ask for and the count of it. Okay. If we wanted the third element, we'd ask for the start point plus one element plus 2 elements. So it's the start point plus 2 elements. So that discrepancy between cardinal and ordinal numbers. 2 is actually our third number. That make sure that's everybody's okay with that, right? 2 is our third number. 0, 0, 1, 2. So there's cardinal numbers, the ones we would actually sit down and do math with and use as numbers, versus ordinal numbers, which is the order they go in, first, second, third. We can't do math with third, or third plus fifth doesn't mean anything. Those are strictly for labeling orders. So we always have that discrepancy of what we ask for and what we count. And then there's another thing where we very rarely work in a single programming language. We mix and match programming languages for what each one has for the optimizations from each one. And not all programming languages do things that way. Some programming languages went ahead and started at 1 just because it's more intuitive to humans. Perl starts at 1 just because it's more intuitive to humans. And some start at 1, also start at 1 because they have other things going on. SQL starts at 1 because there's internal data in element 0. So element 0 is already taken, so we can't, from the programmer side, we can't use that. But that causes a discrepancy because that, well, really no. We're going to see that in a couple weeks, but no matter what programming language we're working in, there's a good chance we're going to mix in some SQL at some point because we want to work with the database. So then we hit that discrepancy of our Java arrays are going to start at index 0, but if we're working with the database, our SQL arrays are going to start at index 1. So they're going to be off by 1, and we have to adjust for one or the other. Which usually isn't much problem, right? One set of square brackets for the indexing gets I from our for loop. I'll jump ahead a little bit to our when we get to examples in about 5 minutes. One of the arrays gets I from our for loop, and the other one gets I plus 1 or I minus 1, whichever way we want to organize it. They line up kind of nicely. Let's see, what else did I have in my notes? Arrays can be any type of thing. I wrote byte here for the first example, so that's easy to draw in the picture. But we're probably more likely to make an array of integers or an array of strings. A string is an array of characters. They already put that one together for us and gave it a different name. So you can do an array of characters, but that's already put together for us and built up with a bunch of methods that will be useful and stuff. So it's one that we usually don't start from scratch, at least not in Java. Custom object. I'll just write custom. We're going to get to that very soon. Actually, we've already started making our own custom objects. Kind of saw that the other day when we call methods so that we don't have to keep saying everything's static. The textbook probably does that in the examples. So whenever you're working on your homework, keep in mind that the textbook probably does that because they just introduced, the textbook hasn't got to the point where where they can instantiate the object, even if it's our main object. They haven't got to the point where they can instantiate it inside itself like we did the other day. So all of the examples from that first introduction on methods are probably going to be static in the textbook examples. So just keep in mind that that's, in the long run, that's bad form. The textbook has to be very formal. They can't jump ahead like I did the other day and be like, okay, this is bad form, so we're going to go ahead and look at the proper way to do it. The proper way in the long run. I guess it's improper as far as
introducing a new topic and then jumping a couple sections ahead. But this isn't a level 1 course, right? There's 2 prerequisites to this course. At the bare minimum, this has to be your 3rd programming course. So I don't mind jumping ahead a little in this class. Definitely wouldn't want to do that in like SDEV 120. That would confuse a lot of people. Strings have stuff built in. I have in my notes here on a side margin, I guess at some point I talked about it, a very, very popular one that you've probably seen in other languages. Since I just mentioned strings are an array of characters. Am I still on the board here? Okay, yeah. So set up an array of strings, or kind of do a similar thing with characters. I'll write SA just to keep it abbreviated. And well, let me do S is going to be a normal string. I'll do the basic hello world and make sure I fit on the camera still. Nope. Gotta move the camera. For a second, I was hopeful that would fit. So that doesn't need square brackets. So just a regular string holding some text-based data, written language, the way we're going to work with a lot of our data. Then we can do string. Then we can set up an array of strings. SA equals S dot split. And then in parentheses, say what we want to split on. If you don't put anything in there, it's going to split on spaces. But if you want more than that, you want to put in a regular expression. So we, in quote marks and square brackets, we put the characters we want to split on. So like a space, which when you're typing it, you can just leave a space there. You can also type \S for the escape sequence that means space, which if it's all typed, it's easy to see the space. And sometimes it's kind of useful to see the escape sequence for a space, or a comma, a period, a semicolon, exclamation mark, and any symbol that we want to split our string up on. There's only a space up here, so that would give us the array where each word is in a different array. Or you put the wildcard character. If you put the wildcard character in there, the asterisk, just the placeholder that the computer will try every possible combination that it knows until it finds one that works in a couple of milliseconds. A wildcard selector in there would just split that up into a bunch of individual characters. That's a very useful one to work in. And the notes added to the margins of my notes at some point when I taught this class before, went ahead and covered that here. It does kind of make sense because that's going to be a very, very common one to do, right? Strings are our written language. That's how we work with things. So probably want to think about those right off the bat. Then multi-dimensional arrays. We'll talk about those here in just a second. Let's look at that syntax-wise, then take a break and then talk about multi-dimensional arrays. So I'm gonna come over here and share my screen. And open up NetBeans. Oh yeah, all the examples, I did it after class the other day. I meant to do it in class, but the examples from class are put on GitHub, so if you want to look back at those and kind of see what we were talking about in class and things. Make a new project. I'll just do something with the main application. We saw the other day how to very quickly get that over into a JSP page. Want to do that? Take all these comments out. I should probably go in and change the template at some point.
We saw Java docs the other day. Those are the comments I'm gonna ask to see, at least on final project, probably not even gonna really pay attention to comments and the weekly homework assignments. I'm gonna ignore them just like comments, just like CPU does. But I will ask for the Java doc comments, the ones that generate a website. We looked at those the other day. And when we do those intermediate submissions on that, just the along the way things, I would like to see to-do comments in there as well. Because those are incredibly useful. It automatically puts the to-do list together, which is not part of the IDE, that's part of the language. So that's both of those Java doc comments and to-do comments are part of the language itself. They're not like something special on an IDE does. So any IDE has to do those things. If we're running in a terminal, we have to, and we're going to compile a lot of our Java code ourselves and run it right there on the Java virtual machine from the terminal. We can still pull up the to-do list because it's part of the language and generate the Java docs. So looking at arrays this evening. Oh, I wrote the syntax on the board already. Kind of like we saw before, we have to say what type of data we have. I'll start with int, that's our basic one. And then some square brackets, which I guess we already saw arrays somewhere anyway. We saw those before anyway. I saw those on day one. So the type of data we have, which the square brackets indicate it's not just a datum, a single piece. We have a collection of data to work with. Some sort of reference name, so we can use it in our code. Call it numbers, and that's going to be a new int. Square brackets here in our semicolon, and you can see the error that's popping up there. Array dimensions missing. You probably know the word dimensions from like 3-dimensional space, right? Or 4-dimensional space, because time is included. Location and time. I was standing there, that location, and now I'm at this location after time had passed. But what dimension means is the technical definition of it. It's very technical definition. Dimension in mathematics is equivalent to like the word in English. It's a starting point. The starting point that references itself. Like if I ask you to define what the word means. As soon as you try to say something, you have to use words to do that, right? You cannot define what word means without using words. Dimension is the equivalent thing in mathematics. The definition of dimension actually refers to itself. The word dimension shows up in the definition of dimension. But the summary of it is the minimum number of parameters necessary to describe something. 3-dimensional space. We need 3 parameters to define something's location. Color space, RGB alpha. Right? We need 4 parameters. We need the red, how much green, how much blue, and how transparent or the opacity level of the color we want to show. There's lots of places where it shows up, but dimension is the minimum number of parameters needed to describe something, which definitely shows up in an array because we have to reserve our RAM ahead of time. So we need to dimension it. We need to say how much space do we need. Let's put 5 things there. And this is the counting number. This is the counting 5. There's going to be 5 things. So that's going to be index 0, 1, 2, 3, and 4. That off by 1 thing. So counting in there. And then just like in the backpack analogy, where I stretch that out to the part that we do intuitively, right? That analogy falls apart there because we look in there and just grab the item we need. But stretching that out, grabbing them one at a time and asking that question, is this what we're looking for? Is this what we're looking for? Whenever we're working with a collection, we're going to loop through the whole thing. We saw for loops. Everything's sort of set up for a countable loop. And I mentioned at least briefly that the difference of when we want to use a while loop or a for loop. A while loop is for when we don't know how many times it's going to run. Obviously, we can use them interchangeably. We can use it either way, but our general rule of thumb is a while loop is for when we don't know how many times it's going to run. A good thing to think about in that case would be like the thermostat. The AC is going to kick on when the thermostat says the temperature is above 73 degrees. We have no idea when that's going to happen. The world's leading meteorologists, the best they can do is some complicated probabilities and give us a good chance that it's, on a given day, the temperature is probably going to rise above 73, maybe in the mid-afternoon, but the best the world's leading experts can do is give us a chance of when we're going to hit that certain temperature. And they often get it wrong, right? So it's a very complicated thing to try and predict. We have no idea when that thermostat's going to kick on, or if it ever even will. It may just, maybe we're in Minnesota and a mild summer in Minnesota, the air conditioner may never kick on once. Or down in Alabama, the air conditioner's probably never going to go off if we have it set to 73 degrees. So we don't know when that's going to happen. That's when we use a while loop. It's just until that condition is met. But a for loop is for when we know how many times it's going to happen. Okay. I use the term we very usually there. I really should say it's for when the CPU knows how many times it's going to happen. We as the programmers might have no idea. We might be as in the dark about that as we are about the weather. But when the CPU goes to run that line of code, it's going to know how many times it's going to happen. And an array is a great example of that. It just gave us an error message for not explicitly saying how many elements we were reserving for this array. So the CPU knows exactly how many times it will run if it loops through that whole array. So anytime we're working with an array, we're going to use a for loop, for in. We saw this before. I is a common one for index or integer. Usually we start with I. That's probably the most common thing. Spelling things out might be a little better form. Depending on the situation, you might want a better reference. We'll see that here. Something else here about that here in just a second. While I is less than numbers length, and what I just typed there does not follow the Java conventions. You might notice that we've only talked about, kind of mentioned them briefly. I was spreading those out across the semester instead of sitting down and giving a list like grammar rules. The camel case, we use methods, and really with the private and public is where that doesn't follow our conventions. Because as you can see, there's no parentheses beside that. If there's just a word, a rule of thumb in most languages, what they've all sort of oriented towards, what fits nicely for people, or has worked well for people. So all of our languages kind of gone this way over the years. If there's just a word, that's a variable. Or a data field is our technical term inside of an object. But a variable, if there's a word in parentheses, that's our method. In particular, that's our call to the method, because the method is really just a variable storing instructions instead of storing data. It stores a variable that stores a set of instructions. And then when we pass in the parentheses, that's saying actually run those instructions instead of just holding them. And same thing with square brackets. The word here, like numbers, is our collection. That's storing a bunch of numbers, and we can pass that around as an entire collection, just using that word, sort of like it's a variable. But when we want any particular one, then we throw in square brackets. So just the word means variable. The word in parentheses means a method,
and the word in square brackets means an array or a collection of some sorts. And one of our conventions will be that data fields should always be kept private. But here we are accessing one like it's a public data field. That's just a carryover from C++, kind of like day one when they were cleaning up C++. Before they even decided they were going to just make it an entire language on its own, when they were just cleaning it up, that's from back then. So it drifts away from our conventions, but it seems like a good place to talk about the conventions again for a moment. Oh, and then I++, most people like the post increment, but remember we can do pre-increment. We have the assignment operators in pretty much every language, the plus equals, which is the same as I equals I plus something. But that plus something plus one is by far the most common. So we have an extra abbreviation for that. Same thing with minus. And with the plus plus and minus minus, we can put it on either side of the I. If it's afterwards on the right hand side, that means use the index and then increment it. And if it's over here, that means increment it and then use the index. But we're working with an array, which means our first element is 0. We start at 0. If we increment it and then use it, we skip right over our first element. So we're pretty much always going to go plus plus, but this is a class talking about Java, so I want to make sure and mention those things. And then we can do stuff with each. We can do stuff. I guess the first thing is probably put things in there, right? Should I do a random number? Yeah, so a random number. That'll take. I'm going to stretch out random numbers instead of just typing it, go over the process that you're going to do when you type code. Because, y'all know what the process is. So let's say numbers, index I, which that part probably looks very familiar, right? The index for the next one we're looking at. And I want to put a random number in here. You're looking at it like, okay, I haven't seen random numbers in Java yet. Y'all know the process. Go to Google, search random numbers in Java. And we get some tutorials. That's sort of a standard introduction, so it's probably going to be lots of tutorials to begin with. I've made the point before, always look at the official documentation first. Oh, here it is, way down here. For something as basic as random, it's going to assume, Google's going to assume you want tutorials. But way down here, usually, is you're looking for more advanced topics, the sort of things you're generally going to go to Google and search for. The Java docs will be closer to the top. And so here's that thing like we were looking at the other day. That website generated from comments in the code. Nice description of it. Class to generate a stream of pseudo-random. It's a machine. We can't get true randomness out of a machine. And if we could never use that machine for something specific. So it's distributed enough that it's going to seem random for all intents and purposes. So numbers that seem random, but not truly random. Allegorically random. It seems random because we're not going to sit down and do the calculation to figure out what they are. Sometimes when debugging though, here it is. There's also a seed. So we can explicitly say what starting point to use for those random numbers. So instead of just to cut that calculation down. So we might not sit down in advance and calculate what they're going to be, but we could seed random numbers with say 4. And then every run of the program, it uses that same starting point. So we know what random numbers it's going to generate. That can be very, very useful when debugging. Actually, that can be critical when debugging. Because if we're looking for errors, we kind of need to know which numbers are going to be So that's what the seed does. It tells us which one it is. So there's a construct. So it looks like we have two constructors to choose from. New random number, strings of doubles, strings of ints. This one looks like it'll probably work for us. So the random object has a next int thing. And obviously the tutorial would have got there a lot quicker. But the tutorial is not going to cover everything that a random object can do, right? It's only going to have that basic starting point. So always look at official documentation first, which is official documentation, so it's going to be a hard read and probably confusing. Then use the tutorial to learn to read the official documentation, because this is basically the user manual. In the long run, you're going to run out of tutorials, right? Tutorials only go up so far. And you're probably wanting to do programming past the level the tutorials go. So you need to know how to make sense of the user manual and learn stuff yourself. So use tutorials to make sense of what the official documentation is saying. Returns the next pseudo-random uniformly distributed int. Oh, that sounds like a good way to fill our array here, but you can see there's lots of different ones there. So we need to come back over here and we need a random object. So I'll come up here and create some new random type of data. I'll call it rand. I'll spell it out. It's almost always called rand, it's abbreviated, but our conventions, I was just talking about the Java convention a moment ago, and our conventions are to spell everything out in camel case. So I'll go ahead and spell it out. Or different things. Could call it him random. This is another very, very common one you will see. This is how Google requires their programmers to write things. Hungarian notation, we use a short prefix at the beginning, and M stands for member of the random class. That's how Google requires things. So stuff Google did will definitely vary from the normal Java conventions, but they're Google, they do what they want. Kind of like the updates. If 10 million people get an update, 9 million of people get a valid update, and the other million get some experimental feature, and they'll collect data on that experimental feature. So there's always a chance that every time you update a Chromebook or something, it's going to stop working for, might stop working for a couple hours until they give you the actual update instead of using you as the experiment group and scientific research. But that's what keeps Google on the cutting edge. That was on my mind because of yesterday's convention. Then this just follows our convention. A random type of data, some sort of reference is a new random. And maybe one or two more times I'll point that out, but I think y'all are probably getting used to that fundamental syntax of how we set up some data in Java, right? Random data, call it random, is going to be new random. And well, it has no idea what random is, so we need to import that. Control-Shift-I and NetBeans will do that. Also the little light bulb over here in the lines. Java.util.random. Or another common one, import java.util. Could type random or put the wildcard selector, because we're often going to use scanners too. Right? Have scanners and random numbers. And if we do a wildcard selector, the computer will just fill the rest of that in afterwards. Multiple ways to do that. So I want to look at different ones by going through the whole process. And now we can use this random thing. Yeah, I just realized that's abbreviated so that in examples, like it's very, very clear which one is the data type, the class, and which one is the object. That's probably why it's always abbreviated, because that's one that it's almost always rand in examples. So we want a new random, and we saw random has a next int, which is right at the top of the prediction list. And notice down here, if I scroll to the next int thing,
returns the next pseudo-random uniformly distributed int value from this random number. If I come back over here to the Java docs, returns the next pseudo-random uniformly distributed int value from this random number. So notice that this is the description showing up there in the predicted text. So you can also get to these, instead of going to Google, pull it up from your predictive text list, which notice how it went away. What I like to do whenever that happens, just go back a letter or two, and usually retyping that period, retyping the dot is enough to pull it back up. Next int. So that'll fill our array up. Let's see what happens when we print that. Now print out numbers. And notice I did not put any square brackets. Just the collection, the actual, the numbers as a variable, which the variable is holding a collection of numbers. When we run that, we get that. Looks strange, right? There's a lot of information there, though. Square brackets, that's what we would expect to see with an array. Well, since we have the code right up there, we can kind of see where I is meaningful. We have, so those first two symbols, an array of integers. At means the same thing as always. At 568 DB2F2. Anybody know what that means? Anybody want to take a guess at what that means? I'll give you a hint. It's on the board. I already wrote it on the board twice. Is that something new in the chat room? Is that the one? When we asked for it, when we were going over that stuff, I said, right, the computer's going to keep track of, okay, maybe this starts at, I think it said 100 earlier to keep the math earlier, but RAM's usually pretty big anymore. Maybe this starts at 894,275 is our starting point, which is just a number. I think computers know the best, right? So that is what we get from our output. That thing that I kept writing on the board. It was not arbitrary. It was not arbitrarily chosen for the notes. We have an array of integers at bit. Well, it's in hexadecimal. So that many digits of hex is kind of a big number, right? But we have big RAM chips. You can sit down and calculate what that is, or Google knows what it is. This in decimal. I was expecting the box. Don't forget X. Oh. Somebody must pay for advertising. Okay. There we go. So we have an array of integers on my machine that's stored at that spot in memory. Your number is probably a little bit different. Google used to put up a box like that. If you put something that was clearly a hex digit, as long as it had the letters, numbers and letters, it would bring up a little box, but somebody must have paid for advertising. Google is an advertising company. It's easy to forget that at times. So that's what I was writing on the board. If we just print out the thing, it's going to say what it is. We can print out any particular one. So maybe element 3 is a random integer, which is random. So if we run it again, we get a different random integer. And it's a random int. So it's somewhere between negative 65 million and positive 65 million. Give or take a little bit to get to a power of 2. So that one gives us kind of a big number. So usually want to do things to narrow that down, and there are versions to do that, but things for you all to look into whenever we get to our actively doing things time. In general, we're going to do what I put up above. Try to do a for each loop. Well, we saw the for loop, so let's look at a for each loop. That way we're covering more types of syntax. Because, well, the two prerequisites for this course both use Python, right? Python actually only has what we call for each loops in other languages. When you all learned that, which is fairly recently, you probably saw the range function, like for I in range or something. That's new. The first 25 years of Python, we didn't have that. We only had for each loops. And some languages, those are nicer than others. You'd say like for, it actually be the word for each, which we actually have that as well. We will see that soon. But our general for each loop is going to be the word. Then what type of thing do we have? I'll do another one of these with strings or something afterwards, but int num colon numbers. So here int looks like it might be referring to an index. But this is like what you're used to in Python. Okay? For going back to Python syntax, because I know everybody saw that in prereqs. For line in some file. Okay? And then line is not an index. It's actually referring to that element. So that's what we have here. It just looks a little confusing. This is the first example. I didn't think ahead, and we have integers here. Probably could have, if we had an array of strings, like if we were doing this with args, we would say for string s and args. So this is actually referring to each element in particular. And then we can print that out as out num. So it quickly prints all 5 of them out. Quick results. Multiple ways to do this. You might want to, we can also format it a lot better too, right? Like beforehand, print an opening curly brace, and then instead of print line, just print that, and afterwards print the closing square bracket. So I think I said curly brace. Put print square brackets around it and take the line break out. So then it looks a little more like an array. I got an extra line in there. Got this line break. We'll try that again. So then everything falls in one line with the that. But we probably want a comma. Oops. Plus a comma. Then separate our things out so that they look, it starts to look more like an array. We just made a method that said print array, which we saw how to do. And we're going to do a bunch of stuff with arrays, so it's probably not a bad idea to do that. Oh wait, we haven't seen generics yet. I'll just leave it up here. That one at the end, though, could be a bit of a problem, right? Because we don't want that comma on the very last one. What I usually do for that, this is what I was originally planning to do before we take a break here. I was hoping in 1 minute, but might be just a little bit more than 1 minute. Is use a normal for loop for int I equals 0, I is less than numbers dot length, I plus plus. We talked about what all those things mean a couple times now. Then print out our number plus a comma, maybe another space, but we only want to do that if I is not the last element. Anything else I need there? Anybody want to tell me? Wait,
System out. Print,
oh, yeah, we'll need that one. I was looking for this one, was what I was thinking about. Because length is our ordinal number, right? Our fifth element is index number 4. So if we're not on index number 4, then we'll print the comma. Otherwise, just print the number. Oh, whoops. And here we have to actually use the index. We could do a similar structure in a similar selection structure in the for each loop. Just personally, I've made typos there enough times because we have to think about what that last element will be equal to, not necessarily the index value. If we do it with this type of for loop, we can do just the index. And then oh, whoops. No line break on that. The normal debugging process, right? Do what you think's gonna work, run it, dig out the errors, fix them. I think everybody's familiar with that stuff by now. But you should see a very solid pattern forming there. We set up our array, and we loop all the way through it, and do stuff each time through. Either look for it or look through the whole thing. Usually, it's going to be more like this. We loop through with a selection structure. The kind of digging through the backpack from the analogy earlier. Like, is this the thing we want? No. Go to the next one. Is this what we want? No. Go to the next one. Is this what we want? And when we finally find it, then we do our processing. So that's general structure of how we're going to use actual arrays. One more quick bug before we head to the break. Is out. Actually, I don't even do that. So numbers, we have 0 through 4. So if we tried to add something to that, send number 3 there at the end. We get an error you will see very, very often. Array index out of bounds. Should make sense. It's a lot of words there. You have to look closely at the screen to read all of them. A whole bunch of words jammed into one, everything's spelled out. But array index out of bounds. So our index is too big. We said we have 5 elements, which means our highest index is 4. So if we needed to put this 6th element in there, our only option is to create an array that can hold 6 elements and copy everything over. We can't make an array bigger once it's created. A couple more things to talk about, but it's probably a good time to take a break. Does 10 minutes sound good to everybody? Anybody have a comment about that? Break time is usually a good time, right? So my clock on my laptop says 7:19. So we will get back to it at 7:29 or 10 minutes from now.